Good. Now we have it. Okay. For in last week I told you that's gonna be the exam was gonna be chapter 22 to 25, right? I thought it's better to go just from 22 to 24. Okay. So yeah, just instead of leave the chapter 25 for the final. So just an update on that. I'm gonna put that in the notes. P07. That's the notes right here. Insert page break, and today is May 10th, 22, Wednesday, and let's see which week is this one. Week 14, number 14. Okay, and let's say here, just to copy and paste, right? Yeah, here you go. It's currently scheduled for this is 17th, yeah, 17th, right? I mentioned that we're going to do chapter 25. We're not going to do that chapter 25, okay? So just up to chapter 24. Okay, and we leave chapter 25 for the final. So exam 3 currently scheduled for May 17, 2023. There we go, put a very boldface. There will be only 3 chapters for this exam 22 through 24. Okay, there'll be only 3 chapters for this exam. Okay. So what else you gotta know? Okay, I corrected. Oh, don't forget to chat for the exam plus labs 5 and 6, right? Labs 5 and 6. Which, by the way, I just uploaded the correction of labs 5 and 6. Check your group folder. The correction is in there. And I also I just upload the corrections of lab 5 and 6. Check your group folder. I also uploaded the spreadsheet for lab 8. Okay, and let's not forget report. One more student coming. Report for lab 7 is due now. Okay, what I want to do, just like I have been doing before, this time today, we will spend the next hour reviewing, not reviewing, but covering chapter 26, which by the way is rather similar to chapter 25. However, keep in mind that chapter 25, which is right, it's more or less similar. Let's put which is more or less similar to chapter 25. More like, which is more or less like chapter 25. However, keep in mind that chapter 25 is a little bit more difficult, okay? Just a little bit more difficult. There's one or another thing that makes it a little bit more difficult. And let's take a look also. And let's see, let's go to Wiley Plus so I can update you what's there, what's in there. Business. Yeah, I posted, okay, I posted homework 9, right? I'm gonna post homework 10, that's gonna be chapter 26. And that's gonna go here. I posted homework 9 on chapter 25. Okay. Soon I will be posting homework 10 on chapter 26. Which is like, which is similar. Let's see. Similar. I don't like that. Similar to chapter 8. He still complain, but that's okay. Let's leave this way. Today you spend the next hour covering chapter 26, which, by the way, is similar to chapter 25. Okay, and let's not forget about, and I will also give you some additional hints about the extra credit, right? But first, let's cover chapter 26, and let's see. 7. I get to the book here. Dashboard. More student opinion. Notification. Yeah, there seems to be some. Okay, can't seem to find the book here. Let me check. Yeah, okay, here. Okay, good. Back here. Okay, this one. Those two chapters are important for those of you who is gonna work with optometry, and because it talks about optical instruments. 26. Refraction of light, lenses, and optical instruments. Okay, we start with the idea of the index of refraction. That's a postulate in geometrical optics. Okay, so let's. That is a postulate, right, or law. or law in geometrical optics about the speed of light, about the speed of light in optical media, right? The first postulate that I didn't mention to you before, okay? There is a postulate. There are postulates in geometrical optics or laws in geometrical optics about the behavior. Let's put it this way: the behavior of light. It doesn't have to be in optical media. Okay. The first postulate, I didn't mention that. I should have mentioned that to you. And by the way, I didn't see that in the book. Okay. This first postulate is the postulate of least time. Okay. Postulate of least time. What does it tell you? What does the postulate of least time tells you? Okay. This postulate states that light travels through space. Doesn't have to be vacuum, doesn't have to be air, but or any optical material, okay? And any optical material by choosing the path of least time, not least space. See the difference? Okay. That's why it's called the postulate of least time. If light has to choose a proper path through space, whatever it is either through vacuum, through air, through glass, through plastic, through water, or a combination of any of those media, light has a mind of itself, right? And it's going to choose the path that's going to take the least amount of time, not the least amount of space. Okay? And that makes a huge difference. It's not as obvious. The least amount of time is not necessarily the same as the least amount of space. Okay? It may, the path that takes the least amount of time is not necessarily the same path that takes the least amount of space, the least amount of travel, the least distance, okay? The least distance or least space or least distance, okay? And I'm gonna give you a quick example. Let's see here. No, not this one. I don't want this one. I want the other one. I want this one here. Okay. There's more students coming. Remember, it's not in the book, but you still have to know that because this is a postulate of physics. Okay, so here you go. Okay. Here you go. Here's a light beam. Okay. One of the postulates of geometrical optics is that if light, let's say, goes from one point to another, I'm going to put this point, another point here. Another point here is going to be here going to be S for source, okay? and here is S prime. If light is reflected here at this surface and is moving in this direction, the path that the light chooses is the path of least amount of time, okay? When you do the math, the proper math, you discover that for reflection, in order for the light to take the least amount of time to go from S to S prime, okay? For the case of reflection, this least amount of time means that the angle of incidence must be equal to the angle of reflection. I switch it here. Let's put it, yep, right here. Okay? And I'm gonna tell you what it's not the light does. Light doesn't do that. You know, a reflected light doesn't travel this way. Okay? From S to S prime. It's not this way that the lights travel, because this is not the least amount of time. Let's see, I'm gonna go right here. Okay, that's the basic principle behind the path that light takes in optical materials. Okay, and I'm gonna put a big no here. That doesn't happen. And this principle, this law, this postulate of least time gives rise to the so-called postulate law of reflection, right? Which, by the way, is not a law, but just a consequence of this other law here, this other postulate of least time. You see the difference? This thing doesn't apply. And I'm not gonna put the angle there, take it out. And I'm gonna take this one out too. Okay. This doesn't happen. Well, get rid of that. This type of law applies not just to reflection, but it also applies to refraction. What is refraction, right? So let's write down what is refraction. Travels through space in optical material through the path of least time, not least space. I'm going to put it very big, not least space or least distance. That's the first postulate of geometrical optics. Then there is this other postulate of geometrical optics that's very important. Another postulate of geometrical optics is about the speed of light. Okay? This postulate states the following. Light travels through optical media, through any medium with a given speed. And this speed depends on the optical density of the medium. Okay, there is something called optical density of the medium. By the same token that there is a mass density, right? There is also the idea of optical density. With a speed that depends on the optical density of the medium. This optical density is quantitatively defined, is represented. Let's put, before we go here, the denser the medium, the slower the speed of light. Okay. This optical density is represented by something that we call the index of refraction. Okay, which, by the way, we represent with the letter N. Okay. And the index of the refraction is defined as get, oh, this one here. Can you remember that? N equal to C. What C? C is the speed of light, right? In the above, C is the speed of light, and V is the speed. C is the speed of light in vacuum. Okay, very important. And V is the speed of light in any medium. For the sake of this course, okay, N is always greater or equal than 1. For the sake of this course, N is always greater or equal than 1. What does it mean? It means that light cannot travel faster than 300,000 kilometers per second. Okay, for the sake of this course. Or go in what I want to do, I want to put yeah, I want to put that right here. Vacuum. Okay. 300,000 kilometers per second. And v is the speed of light in any medium. For the sake of this course, N is always greater or equal than 1. Okay. So those two postulates, just like the laws of Newton, those are the laws of geometrical optics. Postulate of least time and the postulate of geometrical optics. The so-called law of reflection comes from the postulate of least time. Okay, and what exactly does it mean? Let's see if I have a better illustration than that one. Yeah, I must have a better one. Yeah. So yeah, can and come up with this one here. Let's see if you have even better than that. Yeah, unfortunately, I don't have a better illustration. Strange, which is strange. Okay, so let's. Okay. Yeah, illustrate that you want to see something like that. Okay. So suppose that you have a light ray traveling, for instance, from air towards. Here's an example, right? Here's an example. From air, and light traveling in air, is travels 300,000 kilometers per second. Consequently, air has an index of refraction very close to that of vacuum. Okay? And it's traveling from air to another medium. Glass, can be plastic, can be water. What's going to happen? Light, when it enters the other medium, it's going to travel slower than it travels here in air. In the case of glass, for instance, light is going to slow down from 300,000 kilometers to 200,000 kilometers per second, okay? And because of this slowing down of the light is going to bend its path as well. Do you see that? This light ray, instead of going a straight line, when it reaches this the interface of this medium, here it makes an abrupt turn towards the normal of the medium. Towards the normal of the medium, okay? That's what you have to know. This is consequence of the fact that light travels slower in a medium of higher optical density. Okay, so let me give you some examples of index of refraction. And v, the speed of light in any medium, always greater than 1. Okay, examples of index of refraction. Examples of the value. Okay, indices of refraction, indices of refraction. Okay, air has an n equal to 1. Very close to 1 is not equal, it is approximately equal, okay? Vacuum is equal to 1. Vacuum, n is equal to 1. We can even come up with a table here. Insert table. Medium, write down here medium, you write down n. N has no dimension whatsoever. I'm going to put, oh gosh, here you go. I'm going to put here between parentheses, the unit is 1, right? The unit for n is 1. Note from the definition, from the above definition, note that n is a dimensionless quantity. Medium. Okay, we start with vacuum. It's going to be 1. There are a bunch of optical medium out there, by the way. The next one that I already have it here. I'm going to put it in the next page. I'm going to medium. And air. It's very close to 1. It's not exactly 1. It's 1.0000 whatever. Okay, but it's very close to 1. So I'm going to put it here approximately 1. Then we have another optical medium that we call water. This is water's refractive index is approximately 1.33. Glasses, most glasses, not everyone, but most glasses is 1.5. Most glasses 1.5. And diamond, yeah, light also can travels in diamond. Diamond's around 2. Let's take a look at Wikipedia. Oh yeah, we don't need to go to Wikipedia. Oh, it's not 2, it's 2.4. Okay, 2.4, 2.419, 2.419. Oh, not here. Here. See glass, the special type of glass that's called crown, 1.523. Yes, 1.5. Let's see, do they have water here? Should they have ice? Ah, water. The index of refraction of water is slightly different from the index of refraction of ice at 0 degrees C. Okay, and you go. Ice, 1.30, right? You go. Not 30, 1.31. I want 1.309. Let's do like the book. And then there are many other types of medium out there. Sodium chloride, quartz, crystalline and fused. Fused quartz is lower than crystalline. Liquid benzene, carbon disulfide, ethyl alcohol, water. And look at the refractive index of air, right? It's almost 1.000293. But it's air at 0 degrees C at 1 atmosphere. And the other gases are also very close to 1. Okay. And let's not forget that that's the speed of light measured at these wavelengths, 589 nanometers. 589 nanometers, by the way, what's the color of 589 nanometers, right? Let's take a look at the optical spectrum. Okay, 580, we can look here. Let's see, nanometers. How he go? That is so small, it's so difficult to see. You go 589. Okay, 589 is the yellow region of the spectrum. Okay. It's 500 in this case here, 590 times 10 to minus 6. There's something wrong here. Yeah, there's something wrong here with this. He's giving us in meter. Yeah, there's something wrong here with this graph. Should be 10 to minus 9, not 10 to minus. Let's take a look at another book. Let's see, visible light. Yeah, see that? It's in this range, right? It looks like they made a mistake here. It looks like, you know, what they mean here is nanometer here. And looks like a mistake here too. Because nanometers tend to, let's see, 10 to, no, there's no mistake here. It's 10 to minus 6. Yeah, that's right. There's no mistake here because here is in meter. But here, he didn't put it here. Here's in nanometer. Here is correct. Okay. Well, the mistake that he made here, he didn't specify that it's in nanometer. Okay. Every now and then we find those mistakes, even in Wikipedia. They should have specified those values are for nanometers. So 589 nanometers. Now people going back to the book here, right? So you go ahead, use light of these wavelengths, yellow light, and you measure the refractive index of each of those substances. and you get this value. It's possible to measure refractive index. We're not going to go through that, how to do that, okay? But it's possible to measure the refractive index there are devices called refractometers that do that for you. So that's what you have to know. And so if you want to calculate the speed of light in those different materials, all you have to do is to use the equation for the refractive index. 300,000 kilometers per second divided by the velocity in the medium. P is the speed of light in the medium. Not in any medium, but in the medium. And the consequences, like I said, is that when light goes from a medium of lower optical density to another medium of higher optical density, the path of the light is bent. That's why we call it refraction. If you go in my website, you are going to clearly see something like that. It's a picture. It's a real life picture that I took. Okay, sciencesensorstech.com. That's my website. I work with optics. My expertise is in optical fiber sensors. Let's see. Fiber sensor coloring waveguide kits. That's the one I want. Okay, here you go. Here is one medium here that I have. Is plastic. It's acrylic. Okay, it's acrylic, and we can clearly see the path of the light in the acrylic. As the light propagates through this acrylic, it starts to lose intensity because light escapes. But what's happening here? I have my green laser illuminating this acrylic, the surface of this acrylic, okay? So the path of the light from the laser tip would be something like that, right? Before it enters the medium. Okay? But because there's a change in the optical density of the medium, instead of light instead of traveling in a straight line, its path is going to be bent towards the normal of the surface. Okay? Because of the slowing down of the light. Okay? So here you have refraction, but then here you have something else. You have what we studied before. We have reflection. This plastic surface not only refracts light, but it also reflects light. That's why you have this path here. You can see that very clearly, right? And then what happens next? Well, here you go. Light is traveling in the plastic right in here, and it reaches the other side of the medium, and now it's going to travel from a medium of high optical density to a medium of lower optical density. When something like that happens, light, light refracts away from the normal. See that? Instead of traveling at the same angle as before, light is going to speed up, and because it speeds up, it refracts away from the normal. Some of the light refracts, a little bit of the light reflects. That's why you have this reflection here, right? And the whole thing repeats. This light ray is going to refract towards the medium of lower optical density. Consequently, the light is going to refract away from the normal of the surface, and a little bit of the light is going to reflect again, and then we have this other path ray that you're seeing here. Okay, one reflection number one, refraction number one. Okay, I'll call this one refraction number two. Then you get refraction number two, refraction number 3. Reflection number 3. We can draw that. Let's make a drawing from scratch. So you can have that documented there in the good. I'm going to put it lightly. No, it's not what I want. Yeah, it was like that. Like that. Okay. So here you go. We have my green light traveling from my laser towards this medium of higher optical density. I'm going to change the here you go. Higher optical density. At this point right in here, let's put a 45-degree angle here. So it's easier for me to draw the reflection, right? At this point here, you're going to have the first reflection of the light. Don't forget what you saw, that is an actual picture. Here I'm just illustrating. It's a real life picture. And here I'm just illustrating in a drawing so you can understand it better. But in addition to that, you're also going to have a slowing down of this light, right? And because light is being slowing down in this medium, it cannot travel in a straight line. It is going to be bent. Its path is going to be bent in this way. From lower refractive index medium, from lower optical density medium to a higher optical density medium, light is slowed down and bends, and its path is bent towards the normal of the surface. That's the normal here. Okay, angle of incidence here is equal to the angle of reflection, but the angle, and here angle of incidence is a given angle, and then you're going to have the angle of refraction. Okay, and then what happens here? That's reflection number 1. Let's write it down. Reflection number 1. Reflection number 1. And this one here is going to be refraction number 1. When light comes to this interface between those two media, between media of different refractive index, not only is going to refract, but it's going to reflect as well. Okay, like that. I'm going to do better. Angle. Let's see, rotate, size, position, size, rotation. Can rotate that. I want to preserve the size of the arrow so you can have a more realistic drawing. Yeah, looks like I got it. Maybe one more. That's what PowerPoint allows me to do. So here is going to be my reflection number 2. Okay. But in addition to that, you're going to have the refraction number 2. And by the way, this angle here is going to be the same as this angle, okay? Because the faces of this device are parallel. Refraction number 2. And then right here, you're going to have another refraction. Light is going to speed up. And by the way, this refracted light is going to have a path that's parallel to the reflected light, to this reflected light. That's going to be my refraction number 3, and so on. Okay, we have another one here. Reflection number 2. Reflection number 2, and let's see, reflection number 1, reflection number 2, reflection number 3, and so on. That's what you see in that picture. And don't forget, you're going to have my refraction number 4. Refraction number 4 right here. Let's see if we can compare that side by side. Okay, here the laser is a little bit shallower than this one, right? But refraction, reflection, 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 refraction, 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 refraction. Oh, like that. Okay, let's write it down. What time is that? 9:40. Okay. Those are the 2 postulates. Due to this change of speed, changing speed of the light, due to this change in the speed of light, the light paths change direction. The path of the light, the path of the light, the path of the light changes direction. If light slows down, if light slows down, the light ray bends towards the normal direction between the interface of the 2 media, right? If light slows down, going from a medium of low refractive index to higher refractive index, the light ray bends towards the normal to the interface of the 2 media. Okay? So we have those 2, okay? If light speeds up, going from medium of higher. Oh, wait a minute. Yeah, higher refractive index to lower refractive index. And let's not forget another name for that is optical density, right? Another name for a refractive index is optical density. The light ray bends away from the normal direction. All of that is consequence. All of that is consequence of the first postulate. First postulate. So let me illustrate that. Light is taking this path from here to here because it takes the least amount of time to get from here to here, okay? From this point to this point. Any deviation from this point to this point here, from this path, it will take a longer amount of time. So light is smart enough. And it takes the least amount of time to travel from this point to this point. Okay? All of that's consequence of the first postulate. The first, oh, by the way, the first and second postulates of geometrical optics. Another consequence, let's see. The angle of refraction, by the way, the angle of refraction, by the way, can be determined from the so-called Snell's law. And again, I'm gonna put between quotes. It's not a law. In reality, this is a corollary. This is a corollary to the first postulate. And well, I'm not going to derive this Snell's law here. You already know the so-called reflection law. Angle of reflection is equal to angle of incidence. But then how does the angle of refraction relates to the angle of incidence? Okay, that's given by Snell's law. And let's write down Snell's law. It's not difficult to memorize. Okay, so refractive index of the first medium times the sine of the angle of incidence. I'm going to put I for incidence. Is equal to the refractive index of the second medium times the angle of refraction. Okay? This is Snell's law. Recall that for reflection, we have the following equation, which is not difficult to memorize. Angle of reflection, here you go. Angle of reflection is equal to the angle of incidence. You know, the reflection law. Reflection law. So both of them is a consequence of the postulate of least time. Okay, what time is that? 9:46. That's what I want to cover, but remember this one here, okay? Remember this equation here. And you can play a little bit, you know. One good example is the following. Let's do an example before you go into break. Light example. Light is traveling from air to glass. You know, this glass has a refractive index of 1.5. its angle of incidence is 0 degrees. What is the angle of refraction? Of the angle of refraction? What are the angles? What are the angles of refraction and reflection? Reflection is easier, right? But what about the angle of refraction? I'm going to write down the angle of reflection here. You know, angle of incidence is 0 degrees with respect to the normal. So the angle of reflection is going to be 0 degrees as well. What about the angle of refraction? And again, this formula, you can obtain it using calculus, okay? So angle of incidence is going to be 0 degrees, right? Let's not forget that light is traveling from air that has a refractive index of 1 to the glass has a refractive index of 1.5. The angle of incidence is 0 with respect to the normal, and we want to find out this angle here. Okay? But let's not forget that the sine of 0 is 0. Okay? And sine of reflection is going to be 0 as well. Okay, what does it imply? For this specific case, in which you have normal incidence, light is going to slow down, yes, but the angle of refraction is going to be the same as the angle of incidence. Okay, that's for this special case, but then we can do another one. And you're going to see it's not going to be the same. The result is not going to be the same, okay? So for normal incidence, yeah, there's no, the light doesn't bend. The path of the light is not bent. But we still have refraction. Example 2, we're going to do a different one. Light traveling from air to glass. This angle of incidence, I'm going to put here 30 degrees. Let's put 30 degrees. What are the angles of refraction and reflection, right? Well, for reflection, it's straightforward, right? No big deal here. It's going to be 30 degrees. Now, for refraction, it's going to be different. 30 degrees. The refraction doesn't change. We want to find out this guy here. Sine of 30 degrees is what? Is half, right? Let's not forget that, yeah, 1.5. Let's go to the next one. Here becomes 1 divided by 3. And we have this angle of refraction as being the arc sine of 1/3. Arc sine of, then you can go ahead, look at your calculator, which angle does it correspond to. But I can assure you it's going to be less than 30 degrees. Okay, it's going to be less than 30 degrees because it's moving towards the normal. By the way, you know, less than 30 degrees. Okay, 9:51 right now. I want to take attendance. Any questions? No roster. That's the lab attendance. It says. May 3rd, right? May 3rd was our exam. Oh, we had no class meeting on May 3rd. Okay, we skipped. Okay, no class. I canceled the class that day. And then that's today, right? Arthur Pacheco, are you there? Hello, Arthur. Nope, I don't see Arthur here. 0. And next is Elika. Are you there, Elika? I don't hear from Elika. I'm going to put a star. Brianna Valencia. Thank you, Brianna. Justena Youssef. Hello, Justena, are you in front of your computer? Doesn't look like she is. Ashley, are you there? I don't see Ashley here in the list. Okay, Ashley. Yeah. Yeah, I don't see her. Ashley Diaz. Yeah. Next is Natalie Espinosa. I don't see Natalie either. Let's see, Jeanette. Thank you, Jeanette. Randy. Randy Bautista. Thank you, Randy. Noor. Hi, Noor, are you there? Oh, Justena. What, Noor? Justena Youssef, right? Okay, I don't hear from Noor. Next is going to be Kaylee Hernandez. Thank you, Kennedy Lindsay.
Hello, Professor.
Hello. Okay, next is going to be Ryan Ong. Thank you, Ryan. Next is Donia.
Here.
Thank you. Vanessa Bonilla. Thank you, Vanessa. Blanca Hernandez. I don't see Blanca. And Joshua Jimenez.
Here.
Thank you. Noor, okay, thank you, Noor. Is Alika there? Okay. Alondra. Thank you, Alondra. Daisy Mariscal. I don't see Daisy here. Are you there, Daisy? Nope. Yesenia Montes Rodriguez. Thank you, Yesenia Leibelut. Hello, Leibelut. Oh, here. Okay,
Professor,
yeah.
this is Alika. I'm here.
Alika, okay, thank you. Good. So let's see how many students we have. 15. Yeah, good. It's 9:56.
I'm sorry, Professor, real quick. I replied in the chat, but I don't think you saw my reply. Nor, I'm here.
And Nora, right?
Yep.
Okay, I gave you attendance, right? Let's see, Nor, yeah, right in here.
Okay, thank you.
Okay. Good. So let's have our break now. It's 9:56 right now. Here. Break from 9. Now it's 9:57. from 9:57 to, let's see, 10:15, 10:12, right? 10:12 a.m. Okay. I see you in 15 minutes. Stop sharing. I'm back here. And now let's start with the so-called lab, right? Lab number 8. Let's go here at the don't forget lab 7 is due, right? Refraction of light is the lab of today. So let's see, next week is going to be the exam. Then you're gonna have a holiday. So let's do the following. I'm gonna give you, oh, you're gonna have plenty of time to do this lab, right? Lab 8 due the last day of class. Okay, even better, let's see. Let's do lab 8 on the 29th. We're going to do only 8 labs, okay, because we didn't have a class meeting last week. You know, we lost one lab meeting, so we'll be doing only 8. Okay, and this one is going to be our last lab. Have some material to cover, and let's see. Here you go. Refraction, right? Hopefully, we will be able to cover all this material that we have planned for. Refraction of light. Let's see. I think there is something missing here. Interference. I'm sharing the screen with you. Yeah, that's 26. Yeah, we have chapter 27, right? That's missing. Okay. That should be 26 here. 26. I think we're going to skip 27 and get into special relativity. Yeah, let's skip 27 and get into special relativity, and we cover those two. Okay, we're skipping 27, but still keep in mind that's an important chapter, important knowledge to have. But we are running out of time. We have to pick and choose whatever we can cover. Okay, 28. Let's see, special 29. Let's see how it goes. Maybe we still can cover 27. Okay. That's the physics of the 20th century. This is also the physics of the 20th century. Okay. Now I want you to download. Let's start with downloading the lab number 8, right? 1, download spreadsheet in your group folder. And I'm going to get open also. And today's lab is another ohmic element, another non-ohmic element. The diode. Okay, there are you might not know what a diode is, but you must have seen one and must have even handled one. Okay, LEDs are a type of diode. Is a light. LED stands for light emitting diode. Is a semiconductor device that lets current pass in a single direction. That's what a diode is. Okay. So it's a is a valve that lets light, the electricity flows in only one direction. Okay, so we have ohmic elements, just like a resistor, just like regular resistor. And we have non-ohmic elements. You saw the flashlight bulb, bulb. Okay, those are, and the diode, flashlight bulb and the diode. Those are two elements. Those are two non-ohmic elements. And what's ohmic? What's the definition of ohmic element? What's the definition of an ohmic element? Okay. Okay, it is an element. It's an element that has, let's say, resistance, that has a resistance that is constant with current. That's what it is. The resistance does not vary with a given voltage and current. Is even better, is another way to state, right, is an element that obeys Ohm's law. Ohm's law. And Ohm's law is V equal to RI. Okay. The flashlight bulb does not obey this law. Okay, the case of the flashlight bulb, you saw that was more like a third order polynomial, right? So even though they don't obey this equation here, right? It's still correct. I'm going to write this equation a different way so you can understand where I'm going, right? It's still correct to say that R is equal to V divided by I, right? There you go. That's for ohmic elements. For non-ohmic element, non-ohmic element does not obey this equation here, but non-ohmic element does obey the following equation. You know, it's not going to be V over I, it's going to be something else. It's going to be delta V over delta I, which is not necessarily the same thing. Which is not necessarily the same thing, okay? So, but it obeys following, right? So let's go download the spreadsheet in your group. So let's see what else can I tell you about the diode. Okay, the diode is a semiconductor device that transmits current in a single direction. Okay, it does not let current flow in one of the directions. So let's list just all the devices that we have talked about, right? Battery, right? Everybody knows about that. Battery, power supply, right? We talked about those. We talked about cables, right? Regular cables. Cables are the electrical devices that has negligible resistance. Cable. We have resistors. We have capacitors. I told you about capacitors, although we didn't do any lab with a capacitor yet. Well, we are not going to be able to do a lab with a capacitor. Capacitors, what else? Inductors, right? Capacitors and inductors we covered in the lecture. And the flashlight bulb. And now the diode, which, by the way, again, flashlight. Which, again, is a semiconductor device. Let me get the spreadsheet, or not the spreadsheet, the PowerPoint diode. Let's see if I have it here. No. Let's see, P38. Light bulb must be 0.8. Moment of inertia, no. Okay, I'm gonna light up this one. Okay, and now sometimes we have to do a little trick to find files that we do not know where they are located, right? But I do know that this file is located in the same place that this document opened. I just opened. Let's see what's going on here. Browse. Okay, light bulb resistor in parallel. I don't have the diode. 1, 2, 3, 4, 5 resistors in parallel. Huh. Oh my goodness, I don't have it. Yeah. Huh. Lab slide, illustrations. Illustrations. Let me go there. Illustrations, courses. Sorry to take time here, but I will find this in. Why should I have it? See, save as again. Okay, backup. Let's go there. LACCD. Illustration. Not slides. Oh, strange. Ah. Cannot see from inside the document, but I can see from outside the document. That's interesting, isn't it? The same place, see? The same place in my hard drive. Let me show you. I'm looking for 0.8 here. There's no 0.8 here. For some reason, PowerPoint doesn't show me. But when I go to the actual place in my hard drive, where is it? Oh, I find it 0.6. Let's see. Oh, it's 0.6. Ah, okay, okay. It's not. That's why I was not finding it. So it is here. Yeah, that's the one. No, let's see. Not this one. Browse. I was just looking in the wrong place. That's the one I want. Place it. Yes. Now let's open it. Browse 6 diodes resistor. Okay, so here you go. This lab is in a way similar to the one with 2 resistors. The only difference is that we use a different component in the place of the resistor. Let me make this thing looks better for you. No rulers. No rulers. I don't want grid lines. Okay. And let me get a like that. Let's see if I can get that. Oh, that's so shame. What a shame. Let me try something else. Huh. Oh my goodness. There's something here. I'm struggling here to get this thing. Yeah. Got into trouble. Slideshow. Now I cannot control. I'm stuck here. Oh, yeah. Okay. Good. Yeah, I cannot do the slideshow for some reason. Diodes. For some reason, this slideshow here doesn't work the way I want it. Set up a slideshow. Okay, we're gonna do is out the slideshow. Okay, so let's go back here. Here you go. Let's take a look at the internet. Diodes. Here you go. We have a bunch of devices. We have a device here that's called the diode. That's how they look like. This is not an LED. This is just a regular diode that you can buy out there. This device doesn't let current flow in just one direction. Okay, and it shows exactly the marking. This marking here states the direction that the current flows. That this device allows the current to flow. This is the most generic diode that you have out there. Let's take a look at a special type of diode that you have heard. That's called light emitting diodes. LED light. Okay, they look just like that. I have a bunch of those here at home. And now that we can buy, that's one format of the LEDs. They're very cheap. Here is 24 Brazilian reais, right? 24 Brazilian dollars. 24 Brazilian dollars is like 5 cents. 25 cents, right? Or 25 Brazilian cents. So 2 leads, just like your regular resistor. Some devices, more advanced devices, have more than 2 leads. And again, this LED allows current to pass in just in one direction. If you connect this LED in the proper way, the LED is going to light up. You're going to see the LED lighting up. But if you invert the polarity of the LED and connect it to a battery, the LED is not going to light up because it doesn't let the current pass in the other direction. That's how those devices are built. Okay. And we are going to put a device like that in our circuit. We're going to connect a diode in series with a resistor. Let's go back here. Okay, download spreadsheet in your group, battery, power supply. Those are all the devices that I have introduced you to. And oh, there is also what negligible resistance. There is also the proto board, right? They didn't put the proto board here. Oh yeah, there's also the multimeter. Hey, I'm forgetting a bunch of things here in my list. Battery, power supply. Let's put multimeter here. Digital multimeter. Okay. And which other one? Diode, semiconductor device. Oh, the proto board. I'm gonna put the proto board. Those are devices that I mentioned both in my lecture and the lab. Prototype board or proto board. Okay, and in this lab, we will connect a diode in series with a resistor, so we can study how the current flows in this circuit. Okay, that's what I'm going to do. And I need also one of the spreadsheets that we are going to be working with. Labs, raw data, here you go, raw data 8. Lab 8, let's get this one. Is that the one? Yeah. Okay. So we have all those tables. Don't forget to fill up your group number here and your names as well. Plus the date, please make sure you do that. Non-ohmic elements is the diode. For this specific one, I have a resistor one with this resistance. And then I ask my students also to measure the resistance of the diode. Unloaded, right? You take it out of the circuit and measure the resistance of the diode. Ask my students to do that. We are going to vary the voltage with the power supply. And then measure the current. We vary the voltage with the power supply, measure the current, determine the potential difference along the resistor and the potential difference along the diode, and also get the total voltage. Okay, this number here should match this one. And what I have here would be the resistance of the diode if I divide this value by this value here. Notice that the resistance of the diode varies, right? So definitely this is not an ohmic element. I'm going to tell you about that. Hang it there and I'll tell you what that is all about. Okay, so let's go. I have everything that I need here. I have my slideshow, power supply. I have my notes right in here. Procedure and list of equipment. List of equipment. Okay, we start with the power supply. Close that. I don't need that anymore, right? Start with the power supply here. As they appear, as those devices appear, I will start. Okay, cable, red cable, red cable. Next, that's the symbol for the power supply, symbol for the battery, symbol of power source. The red terminal of the power supply is the positive one. Then connect that to the resistor. So there, resist. Oh, let's get rid of some of those. Oh man, oh, it takes a long time. Here you go. One more. Do I need that? No, I don't need that. One more. Let's see, we don't need the light bulb either. Okay, now we have what we need. Take power. Okay, resistor. Oh, before that, we're going to need an alligator. One alligator, right? One alligator. One red cable for now. That's not the final list. One resistor. One resistor. This resistor is going to be connected in series with the diode, and I'm going to use a proto board for that. Okay, so here you go. The diode that I use in my lab is a light emitting diode. Light emitting diode usually have two legs, most of them, right? Not all of, they all have two legs, light emitting diodes. Well, depending on the diode too, if you have more than one. But a diode that has a single color there, it has only two legs. And most of them, they have one leg that's shorter than the other one. Okay? The longer leg is the one that should be facing the positive side of the power supply. Let's see. Okay, let's see if we can see clearly the legs. Okay, see that? This leg here of this diode is longer than this one. A little light bulb that fits in the palm of your hand. If you're going to power this device, make sure you connect the longer leg to the positive side of your circuit. Okay? And that's what I did here. This is the symbol for the LED. This is the symbol for the LED. Is a triangle with this little bar right here. This triangle points in the direction that the current flows. Current flows only from the right to the left in this LED. The circle around here, remember the symbol of the circle. The symbol of the circle means this the symbol is a reference to the symbol of the sun in the sky. The sun provides light, so that's my LED provides light, and my flashlight bulb, right? Everything that you see a circle around the device, it means that that device emits light. So here you go. Did I write down protoboard, one resistor, one protoboard, one light emitting diode, LED. One light emitting diode. Nah, oh, here you go, those two devices in series. And then we close the circuit. Black, one black cable. One red cable with banana terminal, right? One red and one red cable. Yeah, I'm gonna put it here with banana terminal. Two alligators. We need two alligators, right? One alligator for the red cable, another alligator for the black cable. So we close the circuit. At this very moment, we have current flowing in this circuit. And note that the positive is facing the positive side of the positive of the battery is facing the positive side of the LED. And because of that, we have current flowing. Okay. Here's my multimeter. Now I came up with a proper, this is a different multimeter, right? Than the one that we are using. And what we are going to do first is to measure first you measure the resistance. I skipped that part, right? But before you connect everything, you measure the resistance. And going back here, this, yeah, here you go. Measure the resistance of with the multimeter, the resistance of the resistor with the multimeter, and measure the resistance of the diode with the multimeter. And this multimeter is going to be connected to the extreme right of the resistor and the extreme left of the diode. Okay, so you're going to need two red cables and two black cables now. Two red cables with banana terminal, two black cables with banana terminal. Did I write down multimeter here? No, I didn't. Digital multimeter. Okay. And then we're gonna mix, we'll measure the total resistance. The procedure is very similar to the other one. Okay, we start with 10 volts, measure the total resistance, change to 8 volt, measure the total resistance, and so on, right? When we get to this point, we invert the polarity of my power supply to get the negative voltage, and something happens. Okay, well, the voltage is still the same. Okay. You're going to see later on what's going to happen to the current. And those are the measurements that we did for the total voltage. Procedure. One, connect positive of power supply to terminal of the resistor. 2, connect other end of resistor to protoboard, one of the holes to one of the holes of the protoboard. Okay. Connect the resistor in series. Okay, the other end, connect the resistor in series with the diode. Just describing what you saw in there. Close this circuit by connecting the other end of the diode to the power, to the negative terminal of the power supply. Okay. Connect the DMM, okay, digital multimeter. Measure the total voltage of the circuit with the DMM 6. V total. V total. And then you're going to measure the V1 and the VLED, okay? V or VD, right? VD for diodes. Okay, now you're going to see the difference? It's the same circuit that you had before, but now you are connecting. You gotta compare this. I'm gonna copy this one here so you can see more clearly. Okay, that's what we have for V total. All I'm doing here is changing, right? It's changing where? Oh, I didn't switch. I see. I didn't switch here. There's a mistake here in my drawing. Let me fix that. This terminal here of the power supply is supposed to be on the other side. This way. Here you go. Here you go. Yeah. Here you go. What the heck is going on here? Interesting. I'm gonna do that manually. So now I have the right polarity. Okay. Now I'm gonna measure V1. By what? Start with 10, measure V1. Lower the potential to 8 volts in the power supply and measure V1 and so on. When we get here, we are going to, after measuring the volt, after lowering down the voltage to 2, right? We invert the polarity of the power supply. This one is now correct. But again, because it's flowing against the direction of the LED, what you're going to have, you're going to have no current. Because you have no current flowing through the resistor, the electric potential that this guy is going to measure is going to be 0. Okay? So that's what we're getting here. 0, 0, 0, 0, 0, and so on. Oops. Interesting. Yeah. Good. Now I made it. Okay. Think about that. We do have electric potential. Let's take a look at the data again. See here, if I put 10 volts here, the total voltage that you want to measure is going to be 10 to 8, 8, 6, 6, and so on, right? But when you measure the potential, the electric potential across the resistor, which is an ohmic element, since the current is going to be 0, the electric potential across the resistor is going to be 0 as well. Okay? So let's measure the total voltage of the circuit, the DMM. Measure the voltage across the resistor with the DMM, and that's going to be V1. I'm going to write it down here. Note C that when we invert the polarity of the battery, no current flows through the circuit. No, and that's because of the diode, right? Because of the diode. The diode that is a valve that doesn't let the current flows in a given direction. Since current is 0, the electric potential across the resistor must be 0 as well. Okay, but that's only when we invert the polarity. Okay, so here we go. Next, what are you going to do? You're going to measure the electric potential across the diode, right? Which was here, and now you move it there. I'm going to put all those together so you can see how this one, this one, no, this one here. No, I'm gonna put them together. This. Yeah. These and this, yeah, those two. I'm going to measuring current, not yet. Okay. Now, what we did before, right? First, we measure the total voltage of the circuit. Then we measure just the voltage across the resistor. And now we're going to measure the voltage across the LED, the LED. And that must be, okay, I gotta fix that as well. That's the right way of representing it here. I'm gonna move this guy here. Okay. Let's look at that again. We start like that. We measure this one. Not negative voltage. Let me erase that. And then we're doing that now. Let's see what happens when you do that. The data is right in here. Okay, here you go. 1.81, 1.867, 1.837, 1.795, okay, 1.763, and then we have those negative voltages here for the voltage across the diode. Okay. We do have a voltage, but for the resistor, we do not have a voltage here. We do have it here, but not here. And by the way, this voltage here coincides with this other voltage. Since the electric potential is 0 here at the resistor, this voltage here must be very similar to this one, and so on. Because of conservation of energy, right? We didn't finish all the data yet. We collected only the voltage. Now we are going to collect the data for the current. In order to collect the data for the current, we must connect the power supply in series with the DMM, digital multimeter. Red to the plug that measures current in my multimeter. We are not going to use this plug here that's only for voltage and only for voltage. Red cable, black cable, resistor, diode, close the circuit. Okay, that's how we do it. That's how the diagram looks like. I gotta fix that. It's not positive here. Here is negative. There's many mistakes here. Let's go get this guy here fixed. Good. Okay. And then we invert the polarity. When we do that, let's see what the data tells us. Now we're measuring the current. See that? Why the voltage is positive, we still measure some current there. But when we invert the polarity, the current decreases drastically. Okay, because the LED doesn't let any current flow in the other direction. So the current is almost 0. It's not exactly 0, but it is, it's close enough to that. What does it mean? It means that the resistance of your diode becomes very large. That's why it's displaying division by 0. Right here, division by 0 is a very large number. And so it's 10:59 right now. We should start, we should go for another break. Any questions about that? Okay, and let's see if I have another graph here for you, another illustration here for you. Okay, okay, just a comparison, right? Resistor 1 and resistor 2. Okay, so that's what it is. That's all you need. So I'll save this guy, is already saved. And let's go for our break. Okay, break from 11 a.m. to 11:15 a.m. Okay, any questions? If you don't have any questions, let's go for our break, and I'll see you in 15 minutes. Okay, I'm back here. Let's start sharing. Okay, what you have to do this time, you're gonna plot a different graph. Okay, so far, let's see here. Yeah. Go to see what you're gonna do here. No, that's right. What you're going to do here is just to plot the V of the diode versus I, and you're going to see that you're not going to get the same graph that you usually got for the other case, right? It's not a straight line. Okay, it's not a straight line with a slope. It's going to be something like that. And there is, you know, let's see here. Oh, there will be no regression. Yeah, no regression equation here. Okay, there will be no regression equation here whatsoever. And there is no need for CL or R squared. That's all you need to know. That's all you need to do in terms of graphs. Okay, so plot. Procedure. Plot VD along the vertical, along the y-axis, and I along the x-axis. Do everything else that you do, right? And do everything else, and do everything else that you do, which is the units, sig figs, right? Unit sig fig, then that's and unit sig fig, and that's it, right? This one is a simpler experiment, even though it's a different one, but that's, you know, a second example of a non-ohmic element. The diode that don't let the current go through the circuit. If you plot here, I plot the VD, right? The voltage of the diode versus I, but you can do the other way too. I'm going to invert it. We usually, for this type of situation, we do not plot the V against D, against I. We do the opposite. We plot I against B. Okay, and that's what I'm going to do here for you. And then you compare what is available out there. G, here you go. No, there's something wrong here. Oh yeah, I got it. I got the other one. This is I versus VD, okay? And that's how we usually plot a graph for a diode. And VD voltage of the diode instead of VD versus I. Note that the current remains very low, remains at 0. And then suddenly at a given voltage value, the voltage just take off, okay? At a given current value, the voltage just take off very high. And you can look at that in the I versus V graph. Let's see if that's the one for the diode. Okay, must be this one here. Okay. Nope, it's not what I want. For the diode, I versus voltage for the diode. Yeah. Okay, he didn't plot here in the negative region. You can see, right? But the diode, the graph of the diode I versus V of the diode goes just like that. Fortunately, that she's supposed to have the negative too. Oh, right in here, this one. Okay. Oops, what's that? Several cookies. Okay. Okay, so here you go. Here is the current versus voltage for a diode. If you have a negative voltage, the current remains very low in the negative side. But if the voltage is high enough on the negative side, then you have a breakdown of the diode. We didn't get in there. In our graph, we just work it in this region here. Okay, and we didn't get enough points here either. If you had gotten enough points there, we would be seeing this increase right here. But that's what you should get in your graph. Okay, let's go one by one. See if you folks are getting what I'm getting. So instead of plotting, let's see, plot VD along the y, and then you do two graphs, right? Plot I along the y-axis and VD along the x-axis. The IV graph, the so-called IV graph. It's easier to see the behavior of the diode when you plot this graph here instead of the other one. So let's go one by one. Today is 10. Okay, Arthur Pacheco, are you there? No, Arthur Pacheco is not here. Elika, are you there? What happened to Elika? Okay, I'm going to put a little 0 here. Okay, what about Brianna? Are you there, Brianna? And then I'm going to put a star here for Elika as well. She disappeared, right? Brianna, are you there? Oops, let's see. Yes, okay, good. Do you download? Do you download the spreadsheet, Brianna? Yes, okay, so what else did you have to do? Okay, did you plot the graph? Yes, good. Two graphs, right? Did you see that behavior that I showed to you? That you saw, right? Do you have any questions? No? Okay, good. So let's go to the next student. But one more question, Brianna. Did your graph behave just like you saw it here? From here to the left, right? It behaved like that, right? Just want to make sure that you have the right data there. Yes, okay, good. So let's go for the next one. Justena, you download your spreadsheet, Justena? Justena is not here. Oh, well, she left. What a shame. Let's see. I'm gonna put a star here on Justena. Ashley, are you there, Ashley?
Yes, I'm here.
Okay, I'm gonna give you attendance. Did you download the spreadsheet?
Yes, I did.
Okay, did you plot the graph?
Yeah, I'm trying to plot the second one.
Okay, and all you have to do is to invert the axis.
Yeah.
Okay, so I'm gonna put your working on that. Natalie, did she show up? No, she didn't show up. And Jeanette. Hi, Jeanette, are you there? Okay, you downloaded, that's good. And what about the plot? Did you plot the two graphs? Just the first one. Okay, so you're working on the second one now, right? But let's see. So you did plot the first one, right? Yeah, okay, good. Okay, so just invert the axis now. Randy, did you download the spreadsheet? Are you there, Randy? Oh yeah, okay, I did. Good. Did you plot the two graphs? Both of them or just one? Both of them? Okay, so did you see that behavior that you saw here in this graph? Low voltage on the negative, low current, right? On the negative voltage, right? And then that big takeoff. Okay, good. So now you gotta work on the rest, right? Units and thick figs. Let's see, no need to do regression equation. Units and sig figs. Next is Noor. Did you download the graph, Noor? Yes, good. Did you plot the two graphs? I plotted both graphs. Good. Do you see that behavior that you're supposed to get? Okay, good. So you have good data. Kaylee, did you download the graph, Kaylee? Kaylee is not here. What a shame. I'm gonna put star here. Kaylee. Okay, Kennedy, did you download the graph?
I did download the graph and I tried to plot both, but I think that I'm doing something wrong because I'm not seeing something similar to what you demonstrated.
Okay, so let me check group number 3, lab 8.
Thank you.
Group number 3. Group number 3. Okay, so first we plot I and VD, okay?
Okay.
You have the diodes. Insert graph. Okay. Did you get something like that?
So, oh, okay. Yeah, I
Okay.
don't know what I did wrong, but
Okay, so maybe you didn't plot VD. Maybe you got you plot V1 or something else. Okay. And then you gotta invert this data, right? Here you go. Copy this data and no, not add trend line. I don't want that. You want to select data and invert I and I, G and G. Okay. Okay, so right in here.
Right.
So you're supposed to get, so you get exactly the same thing that I showed there. Let's see. I want to put that side by side with my graph that we saw in the website. Right in here. I'm gonna put it. See, this part here is somewhere around here in this negative voltage.
Right.
Okay. This little increase here, I don't have enough data to see that. But the other part that's taking off, I have it. I had to put more data points here to see this little curve here below. Okay. So.
Thank you for the clarification, Professor.
Okay, welcome. Let's see here, 3 and. This one and this one. And I don't want this one here. Yeah. I'm gonna close this one too. Here we go. Next in line is working and Ryan. Did you download the graph, Ryan? Ryan's not here. Oh man, everybody has left. Go. Donia, are you there, Donia? Okay, so did you download the? Did you download the spreadsheet? Yes. Angélica, oh, well. Você mandou mensagem para ela? Okay. Okay. So let's see. Did you plot? Okay, so I presume that you got the right graph, right? We're working on it. Okay, good. Vanessa Bonilla. You download, Vanessa. We have download and plot the graph. Okay, good. So did you see the behavior that I mentioned? The graphs? Yeah, okay, good. So you have good data. So we'll now work on the units and stick figs, right? Blanca Hernandez. Doesn't look like she's here. Okay, Joshua Jimenez.
Yes, I plotted both graphs and they came out the way you showed us an example.
Good, thank you.
Mhm.
And so you can work on the rest. Okay, Alondra. Did you download present and downloaded? Okay, graphed as well. Okay, so I presume that you got the proper behavior right in the graph. Okay, so Daisy, is Daisy here? No. Yesenia? I don't see Yesenia either. No. Okay, I'm going to put a star. Label it. Okay, so you downloaded the graph, is that right? You downloaded the spreadsheet. And did you plot the graphs, the two graphs?
I'm working on it.
I didn't understand. What did you ask?
Sorry, I'm working on the graph right now.
You're working. Okay. Okay, you're working on that. Thank you. So it's 11:34. Okay, I think that the easiest of all experiments because there's not, there's not much things to do. And by the way, let's talk about the I almost forgot about that. Since we have time, let's talk about the extra credit, okay? I'm going to give you an additional hint, talk about the extra credit. Since we have time, and let's go back what I spelled out before. Hopefully you already figured out how to do that. In case you haven't, I'm going to, let's see, I got an extra. I also give you some additional hints about the extra credit. Let's see, extra credit right here. Okay, so extra credit. We're going to do the following way. Extra credit. 29. 29 is going to be Monday. It's going to be the final, right? No, the final is going to be on 31st. Okay, 29. Oh, we're going to have, oh, I see. We're going to have a Monday meeting 2 days before the deadline. Okay, good. So your extra credit is going to be due lab 9 and extra credit due. Okay, so there are some details here. Extra credit. You will require one. You will require some research on your part, and it's due. Okay, extra credit is extra credit is an individual. It's individual work. Okay, individual work. So it's not a group work, it's individual. You're going to okay, lab 2, right? So you're going to rename the spreadsheet to, you know, P07 L02, right? Group, whatever it is, but then you put your first and last name, so I know who you are. XL, right? XLS, I guess. Make sense? That's L2, lab 2. You do the same with lab 7. Lab 7, and name your spreadsheet to first and last name. So I want you to email me these 2 spreadsheets. I prefer that you email me to my personal email address, okay? AOL. On May 29 till, I want to email me 12 noon. Okay, and these 2 were the only 2 labs had to fit. Okay, these 2 were the only 2 labs that you had to fit an equation that was not, that was other than a linear fit. Okay. In lab 2, you had to fit a power equation and a log equation to the same data. Okay. In lab 7, you had to fit a 3rd order polynomial to the data. I'm going to give you some more details. Oh, yes. Yeah, definitely. Let me put here. Pacific Standard Time. Yeah. It's not Brazil's time, no. You know, 12 noon there is going to be 4 o'clock here. So in lab 7, what else? The regression equations that you got are correct, and as well as the R square, Both the regression equation and the R square, both the regression equations and R square are correct. Both the regression equations and the R square are correct. What is not correct? What is not correct is the confidence level table that I provided you, This confidence level table applies only to linear fits, okay? To equations that to regression equations that are linear, applies only to regression equations that are linear. There's a reason for that, and there's a reason for that, okay? So the question is, how can we use, the question is, how can we use the confidence level table that you have, to get the proper confidence level? Okay, that's the question. The way to do that is to somehow, to plot a graph of V versus something else that results in a relation that is close to a linear one. Okay, I'm going to give you a little bit more of hint. We have only 15 minutes to go. Hopefully I'll be able to fit into what we left here with the time that we have left here. Once you do that, you will be able to use the confidence level table that you have. Table that I provided you, okay? Now let me give you some more hints here. I'm gonna bring the lab 2 here. So, okay, let's say, this one here, lab 2. Oh, I shouldn't have that here. Let me erase, right? So for lab 2, let's see. Let me fix that. Let me fix one thing here. The way to do that is to somehow plot a graph of V versus something else that results in a relation that's close to a linear one. Okay. For lab 2, now I'm gonna make things a little bit easier for you. you should do the following. You should do the following. A. Lab 2. Notice that we plot V average versus R, right? That's what we did. V average versus R. I need you to create, to insert 2 columns here. Can you do that? Go back to your spreadsheet lab 2 and insert 2 columns to the left of the average. Let's see, the left of the average. No, you don't need to do that. We don't need to do that. There's something easier that you can do. Let's do something easier. Okay, you're going to do the following. At this column, you go ahead and write power. Okay, and at this other column, you go ahead and write log. Okay, that's the hint I'm providing you. I want everybody to do that. Follow this instruction, right? On cell M17, right? On cell M17, write power. On cell N17, write log. Okay. Hopefully you already, some of you already found out how to do that. There is no need to put the units here. And then what's going to happen? In those cells, you will figure out what numbers are going to come here, what numbers are going to go here, and what numbers are going to go here. Okay? On cells M through M19 through M24. Okay? On cells M19 through M24, you must somehow write the proper numbers that will be used together with a plot with the average. Okay. Similarly, for the other one, on cells N19 through N24, you must somehow write the numbers, find, not write, but find the proper numbers, that you will, the proper numbers that you will use, with the average, right? With the average to plot your linear graph like that. It's not any numbers that you're going to put there. Okay, it must make sense. Here you go, same thing, right? That you will use, with the average to plot a linear graph, Now the question is how you're going to do that. That's the key question. The key question is how you're going to do that. Is how you are going to do that. Okay, that's the key question. Okay. Let's see. Let me put this one is in the wrong place, right here. Okay. For lab 7, you must do something similar. Okay. You do something similar for lab 7. You do lab 2 should, and then once you do that, plot the average, plot not the average, plot power versus the average. Get your R's, get the regression equation and R square. Regression equation and R square. Two graphs, plot log versus average, get the regression equation R square, and find CL, right? And find CL. Repeat. We still have time? Yeah, we still have time. Let's take a look at lab 7 now. Sugar, don't forget. You will need to plot two graphs, right? You need to plot two graphs. And that's lab 2. Let's take a look at lab 7. Lab 7. Right in here. Lab 7, what did you do? You plot the VB against I, right? That's what you did in lab 7. Here you're going to do something similar that you did, that I asked you to do for lab 2. Here you are going to put polynomial. You're going to write down polynomial. And you're going to find, going to create this column, right? With the proper data. You don't need to worry about, say, yeah, in this one, you gotta worry about the units. Just like before, you're going to somehow find out which numbers are going to go into this cells, okay? So that's going to be M8 all the way down to M19. M10 to M19, M10 to M19. Okay. For lab 7, you do the following. For lab 7, you must do the following. You must do the following. On cell M, going back there, forgot it. On cell M8, write polynomial. On cells M10 through M19, through M19, yeah. Through M19. Through M19, you must somehow find the proper numbers that you will use with V, not the average, right? Is that V? Let's take a look here. No, actually it's VB. With VB, yeah. With VB, that you will use with V sub B to plot a linear graph. The key question is how you're going to do that, just like before. Plot polynomial versus VB. Get the regression equation and R squared and find CL. Okay. In this case, you need to plot only one graph. You will need to plot only one graph. Okay. Okay. In order to find the values, the mystery values, right? Let's call it mystery values that goes in the respective column. The places, come on. You will need the following. No, you may, not the mystery values. To complete this task, okay? Not to find, but to complete this task, you will need the following. You will need the following. One, the regression equations of the original reports. Okay, one. So 2 regression equations for lab 2, 1 regression equation for lab 7, right? Definitely you're going to need that. The average for lab 7 and VB. No, for lab 7, this one, lab 7. Okay, for lab 2, the average for lab 7 and VB for labs. The average for lab 2 and VB for lab 7. Here you go. What else? For lab 2, you will need this column here, R average. For lab 2, you will need R average. Cells H19 through H24. Cells H19 through H24, right? Not this one. Yep, H19 through H24. To complete the slide, you need the following. Let's do the following for lab. We're going to do the following. I'm going to put in a more organized way. For lab 2, okay, here you go. The regression equation for the log and for the power and log. Regression equation for the power and log. Okay. The average. Okay. Ooh. The values in the V average, the numerical values in the V average column. Oh, we're running out of time. It's necessary we continue in the next class, okay? You go to numerical values for the average. the numerical values for R in the R average column. Okay, what else do we need here? The regression equation for the power and logs, okay? For lab 7. For lab 7. The regression equation for the polynomial, the third order polynomial. We're gonna need the third order polynomial, okay? The numerical values for VB. Yeah, numerical values for VB in the VB column. The numerical values on I in the I column for the current. Let's go there. 7. VB, yeah, VB and I. Okay, that's all you're going to need to solve this extra credit challenge. Okay, so it's 12 noon right now. And hopefully you already have some idea how to do that. If you don't, just send me some emails. I'm not going to tell you the full answer, but I may still give you some help, okay? Any questions? Okay, so there is office hours right now. And if you stay around, I'll talk to you. Otherwise, I'll see you next week. See you all, and thank you for being here. Oi, cadê você? Melo?